Our first lesson on circles sort of combines two sections in our book, section 10.1 to 10.2, in case you needed somewhere to go back and refer to. The first part is just talking about circles and all the parts that come with them. So if you look at all of these circles in this diagram, they all have a center point at P, and so all of the names of those circles are just called circle P. And you've learned a lot of this stuff. So here is our radius. Our radius is just a line segment, and so that's something that we're going to have to remember. I think I'll name that point A, that we would name a segment with a little segment bar above it. So a radius is always a segment that starts at the center and goes to the edge. A diameter would be also a line segment, but it has to go through the center, and we would just name it by those two endpoints, maybe an A and a B. A chord is sort of like a diameter, only it doesn't have to go through the center. It's just any line segment that connects one point on the circle to another point on the circles. Maybe I'll call those points C and D. So that would be chord CD. Again, it's a line segment. A secant is related to a chord. A secant, though, is a line. It's a line that intersects the circle. It hits the circle in two different places. And so maybe, you know what, I'll call that point C and that point D again. And so the only difference between a chord and a secant is that a secant is the entire line. So a chord being the segment, a secant being the line that goes through. Now, if you had a secant that didn't actually touch at two different points, but just barely touched, let me try again. Just barely touch the circle, just on the, it stays on the outside, right? It just touches the circle at a certain point, and I call that point where it touches the point of tangency. That line right there is called a tangent line. A tangent line is not super related to SOHCAHTOA type tangent, although there is a connection there, but a tangent line is just a line that touches. So we would have to name some other point on that line. Maybe I'll say G. So line TG would be a tangent line. Or you could even say that segment TG is a tangent segment, but normally if we say tangent, we mean the line. And then major and minor arc. So let's put a couple points here. I've got a point A, I've got a point B. Minor arc, I've got a point A, I've got a point B. The difference between a major arc and a minor arc are that the major arc is the one that goes all the long way around the circle, where a minor arc is less than half of the circle. So the only tricky part about that is how should we name this part of the circle, this major arc, versus the minor arc. And so what we do is for the minor arc, we're just going to call it arc AB, and we literally just put a curvy line on top. Now, if we tried to call this one arc AB, it would mean this short little distance right here, which is not what we're trying to do. We're trying to do this entire distance. And so what we do is we just pick any point that you pass through on your way to B, any point over there. Maybe I'll call that point C. And for a major arc, you're going to use three letters. A, C, B would be one way we could name that major arc. So if you pass through A, then C, then B, you're headed in the right direction. Or we could call that arc B, C, A, either way. Some properties that I want you to know. Let's say we draw a nice tangent line here that just barely, it can just barely touch the circle, right? And so it's touching at this point of tangency. There's kind of a cool thing that comes with an angle here. If you draw the radius in from P to that point of tangency, anybody want to guess what this angle equals? It is a 90-degree angle. A 90-degree angle. How neat is that? 90 degrees. And so we can always say that the radius and the tangent line are perpendicular. abbreviation for perpendicular. And actually that makes our next method of solving problems really neato. So here's another tangent line, a length on a tangent line. And that's sort of related to that tangent segment idea that I talked about earlier. We can actually figure out the length from T to G if we know a little something about the radius, and we'd have to have a little more information, but do you guys see the triangle I just drew? That would have to be a right triangle because tangent lines and radii are perpendicular. And so we are allowed to use the Pythagorean theorem on these things. If you have the radius, which I'm labeling as A, and the tangent segment's length would be B, and then this entire thing would be your hypotenuse right here. So this entire thing would be like a radius plus this little outdoor section. So if you added all of that together, that would be the hypotenuse of this triangle. And then you can just use, since it's a right triangle, the Pythagorean theorem. Neat. Arc measurements. All right, so if we were looking at arc BC right here, arc BC. Now that definitely has a length, even though it's sort of a curvy length, but what I want to talk about is its measurement. We say that the measurement of that arc, and we write it like this, we write it like this, the measurement of arc BC, we actually measure it in degrees. And do you see this angle in here from B to P to C, angle 122? The 122 degree angle, we actually use that, it's called a central angle, and we use that to define the measurement of our arc. So that's a 122 degree arc, if you're talking about its measurement. We could also talk about, what if we looked back here, arc AD. Well, if this is a 122, we could use vertical angles, and that would be a 122. In fact, couldn't we find out all of those central angle measurements? Like this one right here? If you look at this linear pair, the 122 plus something would equal 180, right? That something would be 58 degrees. So this entire side is 180. And if that's a 58, then this is a 58. And so we can basically find out lots of different arc measurements. So I could say that the measurement of arc AD over here is also 122. Let's try a major arc. How about the measure of arc CDB? Can you figure out where that is? CDB. So we're going to keep it curvy the whole time. We're going to go from C to B, but we're going to pass through D on the way there. It's more than half the circle. CDB, that's this arc. And so the total measurement of that arc would be whatever the 58 plus the 122 plus another 58 would be, right? So 58 plus 122 plus 58, so that'd be 180. Is this, oh, no. 238, does that sound right? I think so. Or another way you could check is, isn't that the entire circle except for the 122 over here? So we could think that would be the entire circle minus the 122. Would that be 238? I think so. So the main takeaway here is that the central angle is equal to the arc measure. An arc measure is measured in degrees, just like central angle is measured in degrees. That's a little bit different than arc length, which is this last box right here. The length of an arc is literally talking about how far it would be walking from point B to point C. And we like to relate that to the circumference. You guys know circumference? Circumference is 2 pi r. Or on this triangle, or sorry, this circle, it looks like it's 2 times pi times 6 is the radius, yeah? All right. What is 2 times pi times 6? 2 pi 6. is like 37.7-ish. So that'd be if you walked all the way around the circle, it would be 37.7 feet. Our question is, what if you were just walking from B to C? And so the trick there is that it's only a fraction of the total circumference, right? And that fraction is equal to whatever fraction 122 out of 360 is. So all we have to do is we have to take 122 out of 360 and multiply that times our 2 pi r. So we take 122 over 360 times that 2 pi 6, and that comes out to about 12.8 feet. I'll just write that formula over here for you. Arc length, they'd have to say the word length, is going to be the measure of your arc divided by 360 times the circumference, 2 pi r. Or if you're a pi d kind of kid, you could use that too.